Welcome to the UPC++ tutorial. I'm Damien Roussan, and I'll be presenting today with Kathy Yellick and Amr Kamal. UPC++ is a programming environment for distributed memory C++ applications. UPC++ provides a library that supports asynchronous remote memory access, or RMA, and remote procedure call, or RPC. We'll present details on these terms in today's tutorial. You can obtain all of this tutorial's materials, including the exercises and the slides, at the URL shown here. We'll start by thanking everyone who has worked to produce UPC++, primarily the Pagoda Group, funded by the U.S. Department of Energy's Exascale Computing Project. Also listed here are some of our collaborators who have written the UPC++ applications that we'll present today, and people who have worked on the implementation of UPC++ and the design of the interface. We'll present performance results today from the National Energy Research Scientific Computing Center, NERSC, and the Oak Ridge Leadership Computing Facility, both funded by the Department of Energy Office of Science. Today's tutorial will include material from our SC20 UPC++ tutorial, along with updates based on more recent work. For the first part of the technical content, I'll hand off to Kathy Yellick.
Why should you care about UPC++? Well, it supports applications that involve asynchronous updates to irregular data structures. What do I mean by that? You might have adaptive meshes in which you're updating boundary regions in neighboring meshes, sparse matrices that are data dependent in terms of the pattern of communication, hash tables and histograms that need to communicate data to other processors based on the value of the key that's being hashed or counted, graph analytics, where the structure of the data is really what you're trying to understand in that analytics application, and dynamic work queues that are used for dynamically load balancing tasks in a parallel application. So these applications have a degree of irregularity and unpredictability about the data movement in them. That occurs in space, meaning that the pattern of which processors are going to need to get data from other processors is not known in advance. It may not even be available into the middle of the application, such as when you are putting something into a hash table. It's also irregular in time in the sense that you don't know when that value is going to be put into a hash table bucket. And finally, the size of the data may not be known. It may be dependent on exactly what's happening in the computation or the shape of the data structure that occurs at runtime. There are also architectural trends that motivate UPC++. As we look forward to the exascale systems that will start appearing next year, or look at the pre-exascale systems that exist today, some trends have shown up relative to systems over the last decade or two. The number of cores per node has been growing steadily. The cores are getting simpler, including the cores that exist on accelerators such as GPUs. The memory per core is dropping, and the latency between nodes, the communication latency, is not improving. So we need to do something to reduce the cost of communication in software, but without blowing up the memory footprint. And so we need to overlap communication to hide the latency, but we also need to reduce the memory footprint by using more frequent messages. We also want to have very lightweight messages. If we're going to send more frequent messages due to the memory constraints, we're going to have to make sure that each one of those messages is very fast, or at least has very low overhead, and then we overlap the latency part of the cost. And so we'll want to use very simple messaging protocols such as RDMA, which I'll talk more about. To reduce the overhead of communication, we're going to use what's called one-sided communication, which means we're going to allow a process to directly access another process's memory through what's called a global pointer. What does this mean? Well, if you contrast this with send and receive models, such as in MPI, there's no need to match a send with a receive in a one-sided model. You can't have an unexpected message that is a send without a receive, and we don't have to guarantee that the messages are delivered in any particular order. So to give you a little bit better idea of this, we'll look at this little cartoon of what a two-sided versus one-sided message looks like. In both cases, you're sending some data from one process to another process. And the other process has a network interface, it's got a CPU and some memory. In a two-sided message, there's some metadata, which I've approximated here by saying it's a message ID. There may be other information about what communicator it's part of if you're in something like MPI, or other information about the sender and things like that. That metadata is sent along with the data payload to the other processor. But fundamentally, the information about where that data should be put into memory on the remote CPU and the remote process really resides in the host CPU on the other side, that is in the remote process. And that remote process has to say receive, because that receive is what tells it where to put that data in memory. In contrast, a one-sided put message, so a remote write message, has an address in it as well as some data payload. It may have some other information as well. I'm oversimplifying here, but fundamentally it has the information that a smart network interface can take that one-sided message and directly write it into memory without interrupting or otherwise getting information from the host CPU. So that's the advantage and the reason that it actually has lower overhead to do one-sided communication. And you may ask, well, are network interfaces smart enough to do this? And the answer is yes. All of the exascale and pre-exascale machines, but also any kind of an InfiniBand cluster, most hardware is going to have support for remote direct memory access. This allows us to, by the way, make the machine, even though it's physically got distributed memory, to look a little bit like shared memory. It means that we can have shared data structures with asynchronous access to them. And we'll see what that looks like in a minute when we start putting together the programming model, UPC++. Before talking about the programming model, let's look at quantifying the benefits of this one-sided versus two-sided communication model. And what we're seeing here is the bandwidth for various message sizes on 4 different machines with 2 different networks. On the left-hand side, we have the Aries network, and on the right-hand side are InfiniBand networks. These are bandwidth plots, so up is good. This is not running time. And what we're showing here is the two-sided performance in the dashed green line and 4 different implementations of a one-sided protocol, either a put or a get, and either implemented in GasNet, which is going to be the communication layer underneath UPC++, or in MPI, which is in its MPI RMA model. And what you can see in each of these graphs is, for the most part, the two-sided model is consistently slower in this range of, say, 1K to about 16K messages. Now, eventually on each of the architectures, you should be able to get to peak performance with any of the models, and that's true on all of them except the Cori 2, which is the Xeon Phi, the KNL nodes of Cori. But typically on most machines, we'll see all of them asymptoting to the same line. The one exception in where we see some difference, where the two-sided model is being is actually faster than the one-sided model, is looking at the MPI implementation in the lower right on this system called Gomez. In that case, it looks like the MPI one-sided, the RMA implementation, probably needs to be optimized further. But in general, we're going to see, especially for these medium-sized messages, which, as I said, will be increasingly important due to the memory footprint of these applications and the shrinking memory size in the applications and the lack of improvements in latency costs over several decades of these types of parallel machines. Now, how do we put this into a programming model? Well, we'll call this a partitioned global address space model. And in order to see how it's put together, let's look at the picture at the bottom. So with each process in this program, we're going to have a private segment of memory and a shared part of memory. The private segment you can think of as places where your stack variables will typically go. Other things may go there as well. The shared memory segment is where we're going to put data structures in there that we want other processes to be able to access directly using this one-sided communication. So the union of all those shared memory segments associated with each process is called the global address space. Now, in order to get access to that, we'll use special kinds of pointers called global pointers, and those global pointers will be able to point to things that are in the shared memory segment, but those pointers will also have information about which process that object that is pointed to has affinity to. That is, which process is it nearby? It was allocated. Typically, when you allocate an object, it's going to go into the shared segment associated with the process that does the allocation, and then we can have pointers that other processes use to access it. So this gives you something that looks a little bit like a shared memory programming environment, like you might see with something like OpenMP or POSIX threads on shared memory or multi-core hardware, but it's actually different in the sense that the pointers in this case, these global pointers, are going to encode the affinity information of where the object that pointer points to is, what process that it has affinity with. And that's going to be very important to allow programmers to optimize for locality and allow you to write scalable applications that can run on hundreds of thousands of processes. So just to summarize, this partition global address space, or PGAS model, supports the idea of global memory, takes advantage of the hardware that I mentioned exists in these modern systems, this RDMA hardware. It has the distinction between private and shared memory, which will also be important for optimizing for performance. And then it gives you this lighter weight communication because it separates the synchronization that you get with something like a send and receive model from the data movement. There are a number of other languages that provide this PGAS model that includes UPC based on C, a language called Titanium we worked on a number of years ago at Berkeley that's based on Java. The Chapel language from Cray, the X10 language from IBM, and the CoArray Fortran language. In addition, there are other libraries similar to UPC++ that provide this PGAS model. Habanero UPC++, OpenSHMEM, CoArray C++, Global Arrays, Dash, and MPI's RMA model, which I already mentioned. So we're going to talk here about UPC++, which is this C++ library for exposing this PGAS model to programmers that was developed at Lawrence Berkeley National Laboratory. So what is the execution model for UPC++? Well, it's very similar to MPI's typical model, which is a single program, multiple data, or SPIMD model of execution, where we have a fixed number of processes and they run the same program, but they're not synchronized lockstep. So for example, at the start of a program, if we're running this little main function here, we're first of all going to initialize the UPC++ runtime system. Then we can do a print statement, and that print statement will happen in parallel. As you can see here in the picture, there's a barrier statement, similar if you're familiar with MPI, with what's in MPI, and then another print statement that's only going to be executed on processor 0, which in UPC++ you can find out if you're process 0 by asking if your rank is equal to 0. And then you clean up the runtime system by calling UPC++ or XX finalize. So all these UPC XX things are in the programming model for UPC++, and these are just the different examples of some of the basic primitives that you get. I've been talking about global pointers as a way to access data that's in the global address space. So global pointers can be used to create logically shared but physically distributed data structures. In the picture below, we have a linked list that's living in the global address space. There's one node living in each of processes 0, 1, and 2, and they're linked together with what are called global pointers. There are also global pointers that live in the private part of the address space but point to things that are in the global address space. To declare a global pointer, we'll declare it sort of as we do a C++ raw pointer, that is going to be parameterized by the type of the object it points to, and we'll do this using the C++ template syntax, so global pointer of the type, in this case, double. So we will still have traditional C++ pointers, which we'll call raw pointers here. And that in the picture is the little L pointer. And the L pointer can still point to the global address space, but it can only point to things that have affinity with that process, that private memory. And so the affinity then of these pointers in a global pointer identifies the process that created the object. If you recall, I said that when you allocate an object, it's going to be put in the part of the address space, the segment of the address space that's associated with that process. The global pointer then carries the information about where that object lives in memory, its address, and the affinity for the data. Whereas raw C++ pointers, they can only be used on to refer to objects in the global address space that have affinity to that process, as you can see in the picture here. So how does UPC++ deliver the PGAS model? Well, it is not a language in the sense that it doesn't have a compiler. It is a programming model or a programming system, and it uses the library. This was a design decision made early on in the UPC++ design because it leverages then some of the features of C++ and actually makes it much easier both to implement the language, but also allow it to interoperate with other C++ libraries. So it relies on GasNet-EX that I've mentioned GasNet before. The exascale version of that is called GasNet-EX for very low overhead communication. It's going to utilize those RDMA features. In addition, GasNet-EX provides something called active messages, which are a very lightweight form and somewhat restricted form of a remote procedure call. That is the ability to put some computation on the other processor. And we're going to build in UPC++ a more general RPC or remote procedure call mechanism on top of those very lightweight active messages. GasNet-EX is highly portable across laptops and supercomputers, vanilla clusters, Ethernet clusters, as well as InfiniBand clusters and things like that. So that allows you to write code for your laptop and then run it on any one of those other types of platforms. UPC++ is also designed for interoperability. That was also a design decision made early on in the by the UPC++ and Pagoda team that they really wanted to have interoperability. They wanted to have a process model similar to MPI so that you could have a parallel application written partly in MPI and partly in UPC++. Very important for hybrid applications that want to, for example, take an MPI application and perhaps just add UPC++ to a particularly irregular part of the computation. I mentioned earlier this one of the applications that is actually looking at the deep subsurface modeling. That's an entirely C++ MPI application that calls libraries like Scalapack and things like that. But one irregular piece of it was constructing this big distributed irregular matrix or sparse matrix with irregular communication. And that piece of it was then written in an earlier version of UPC++. UPC++ also allows you to mix in OpenMP and CUDA, and just as you can do an MPI plus X model. So how does the performance of GasNet-EX compare to MPI's one-sided model? We saw some of this data before, but here we're highlighting the latency advantage just for sending very small messages, so 8-byte messages. And you can see that for both put and get, puts are shown in blue and this turquoise, and the gets are shown in red and then magenta, that the GasNet implementation outperforms the MPI RMA implementation on each of these 4 different systems. So the Cori system, the Summit system, and then the Gomez system. And this is the 2 different partitions of the Cori system, looking at the Cori 1 is the Haswell nodes and Cori 2 is the KNL nodes. So you see that advantage in latency. Overall, that corresponds to an advantage from just a few percent, so really sort of negligible, up to about 50% advantage on the 2 different types of communication events. Now, MPI RMI is an end-user programming model, so you might also wonder what happens when we put UPC++ on top of GasNet. Do we preserve that performance advantage? And what you see in this slide is indeed, you do still get faster performance out of UPC++ in terms of latency on the left-hand side, and then in terms of flood bandwidth on the right-hand side from the UPC++ implementation compared to the MPI RMA implementation. So what does UPC++ offer? It offers you asynchronous behavior through these remote memory accesses, which we've talked about here in terms of get and put operations that are that allow you to get access to a remote location in another address space and another partition of the address space. And it gives you very low overhead, zero copy, one-sided communication. It also gives you RPC, which we haven't really talked about, but we'll look at a little bit later in this tutorial. That moves the computation as well as moving the data to another processor. Now let's look in a little bit more detail at this RMA implement, what it looks like. And by default, when all of the communication operations in UPC++ are split phase, that's to try to ensure that you get maximum overlap of communication with either other communication events or with computation. So we initiate an operation and then wait for its completion. The way you wait for it is to have something called a future, which is going to hold the value and the state of whether it is ready or not ready, the value that comes back from a communication event that returns some value. So this is the syntax that's shown here. We've got a global pointer declared that's pointing to an int, and we do a future on that to do an rget into that int. And so the type of the return value here is not just simply an int, which is what the pointer points to, but is going to be this future object, which you can then use to do unrelated work without touching F1, and then later ask to wait to make sure that get has come back, the rget has come back. And so this picture on the right shows is that this data, the 123 value that's living in the global address space, is being copied over into the private part of the data, the address space in the executing processor here. And that happens once that happens, then there's also information stored that it's ready and the F-wait will complete. So ideally, you're doing enough unrelated work that you don't worry about the latency at all, because by the time you've finished your work, that the wait will be immediate. So what about remote procedure call? Well, this is a little bit more complicated. So we've got our initiating processor and our target processor. And remember, we want to both send data, the arguments in this case, to the function, and then send the computation itself. So the syntax is shown here. It's UPC XX RPC, which gives a target process and it gives a function pointer, and then in this case, two arguments. So the initiator injects the RPC to the target process. It goes over to the target process, and the function now will execute, has to have the information about what that function is, and it'll execute that function on the arguments that were passed on this process over here. And when it comes back, it will return some information for the future, which is living on the initiating process side, so that the results can become available to that initiator. You can have many RPCs active simultaneously, even from a single process, and that is going to be used to hide latency, as with the rget operation that I showed you before. So here's a simple. So you've seen some of the basic primitives for writing a UPC++ program and now could write something. And I think that's a good time to actually do that. You need to know how to build and run your application. So this slide shows you the syntax for running the compiler, which is really a compiler wrapper. That is, it calls the normal C++ compiler, but makes sure that the necessary libraries are linked in and so on. And you've probably seen that if you've used MPI with their compiler wrappers as well. For more sophisticated programs, we also provide, UPC++ provides the UPC-XX meta package and the CMake package. And to run the application, then you can use UPC-XX run, which takes in a number of processes that you want to run on, as well as the executable. Again, there's other arguments associated with this that would be familiar to you if you've used other similar tools. And there's also support for various platform-specific launching mechanisms, such as srun and so on. So at the Department of Energy's Office of Science Centers, ALCF, NERSC, and OLCF, these are the module commands that you need in order to run UPC++, to compile and run UPC++ applications. And there's more information and examples for all 3 of the centers that are at this wiki site. I will also say that you can also download, and there's information about how to do this at the wiki site, how to download your own UPC++ installation, say to run on your laptop. It will run on most laptops, on workstations, and on other types of clusters with various types of networks as well. So for your programming exercise, let's go back and revisit the Hello World example. In this piece of the code, what we saw before was after setting up and then shutting down the UPC++ runtime, and by the way, this version of the code now shows what you need to include in order to write a UPC++ application. And when the print statements happen here in an arbitrary order. So our first recommendation is that you go ahead and just take that code and compile it and run it on your favorite system. As I said, all the information is available in this link. And once you have your environment set up and have copied the tutorial materials here, this just shows you how to get into the directory with the exercises and the make command that you need in order to make the executable for the Hello World example. So that should be pretty straightforward once you've got everything set up on your system. So the first real exercise then is to make an ordered version of this Hello World program. So modify the program and have it have a loop that is going to have each one of the processes take turns in order running the print statement. You can use a barrier to perform a barrier which prevents any of the processes from continuing until the other processes have reached it. You might be familiar with that from MPI or from OpenMP. And so we recommend that you do this. It should just take a couple of minutes to do this once you make sure you've got UPC++ set up on your local environment or know how to use the environment on one of the HPC systems. And with that, I think it's a good time to take a break. We'll let you go ahead and try this out. And we'll be back in a little while, and Amr is going to talk to you more about RPCs and some of the more sophisticated features of UPC++ that we haven't really talked about yet. Thanks very much.